Welcome to our comprehensive guide on edge computing interview questions and concepts. Edge computing is revolutionizing how organizations process data by bringing computation closer to data sources. Today, we'll explore 4 critical areas that every technology professional should understand. First, latency reduction, the ability to minimize response times by processing data near its origin. Second, local processing, performing computations directly at the data source for immediate insights. Third, Internet of Things integration, seamlessly connecting various smart devices and sensors. Finally, distributed systems architecture, designing robust computing networks that span multiple locations. These concepts form the foundation of modern edge computing implementations. Edge computing represents a fundamental shift in how we approach data processing and analysis. Unlike traditional cloud computing where all processing happens in centralized data centers, edge computing brings computation and data storage closer to the location where it's needed. This distributed approach offers significant advantages. The primary benefit is reduced latency, enabling near real-time responses for critical applications. Lower bandwidth costs result from processing data locally rather than transmitting everything to remote servers. Enhanced data privacy is achieved by keeping sensitive information closer to its source. Finally, improved reliability comes from reduced dependency on network connectivity to central systems. These benefits make edge computing essential for modern applications requiring immediate response times. Edge computing follows a 3-tier architecture model that efficiently distributes processing across different levels. The cloud layer represents the traditional centralized processing and storage infrastructure, providing extensive computational resources and long-term data storage capabilities. The edge layer serves as the intermediate processing point, positioned at the network edge to handle local computations and reduce the load on cloud resources. The device layer consists of Internet of Things devices, sensors, and smart endpoints that generate data and require immediate processing responses. Data flows seamlessly between these layers, with the edge layer acting as an intelligent filter that processes urgent requests locally while forwarding complex analysis tasks to the cloud. This architecture ensures optimal resource utilization and response times. One of edge computing's most significant advantages is dramatic latency reduction compared to traditional cloud computing approaches. Edge computing achieves response times of 1 to 10 milliseconds, making it suitable for applications requiring near real-time processing. This represents a 10 times improvement over cloud computing, which typically experiences latency of 100 to 500 milliseconds due to network distance and multiple routing hops. The reduction in network hops between data source and processing location directly contributes to faster response times. This performance improvement is crucial for applications like autonomous vehicles, industrial automation, augmented reality, and financial trading systems, where even millisecond delays can have significant consequences. Understanding these performance characteristics is essential for designing effective edge computing solutions. Local processing represents the core functionality of edge computing, enabling intelligent data handling at the source location. The process begins with data collection from various sensors and Internet of Things devices distributed throughout the environment. Real-time filtering and validation ensure data quality before processing begins. Local analysis and computation transform raw sensor data into meaningful insights without requiring cloud connectivity. Decision-making occurs directly at the edge, enabling immediate responses to critical conditions or events. When necessary, processed results are sent to cloud systems for long-term storage or further analysis. A typical edge processing function monitors sensor data against predefined thresholds, triggering alerts for critical conditions while performing local analysis for normal operations. This approach minimizes network traffic and ensures continuous operation even during connectivity issues. Internet of Things integration forms the foundation of modern edge computing ecosystems, connecting diverse devices through intelligent processing hubs. The Edge Hub serves as the central processing center, coordinating communication and computation across all connected devices. Temperature sensors monitor environmental conditions and provide real-time data for climate control systems. Security cameras capture and analyze video feeds locally, reducing bandwidth requirements while maintaining surveillance capabilities. Smart lights respond to occupancy and ambient light conditions, optimizing energy consumption through local processing. Vehicle sensors collect transportation data for traffic management and autonomous driving systems. Network gateways facilitate communication between different device types and protocols. Industrial equipment integrates with edge systems to enable predictive maintenance and operational optimization. This interconnected ecosystem demonstrates how edge computing enables seamless Internet of Things integration across various industries and applications. Distributed computing architectures in edge environments rely on specific patterns and components to ensure reliable operation. Mesh computing creates interconnected networks where edge nodes can communicate and share processing loads dynamically. Hierarchical processing organizes edge nodes in layers, with each level handling different types of computational tasks based on capability and proximity. Federated learning enables machine learning models to be trained across multiple edge locations without centralizing sensitive data. Microservices at edge break complex applications into smaller, manageable components that can be deployed and scaled independently. Event-driven processing responds to real-time events and triggers appropriate actions across the distributed system. Key components supporting these patterns include edge orchestrators that manage resource allocation, container runtimes that provide isolated execution environments, service mesh for secure communication, load balancers for distributing workloads, and data synchronization mechanisms for maintaining consistency across distributed nodes. Understanding common interview questions helps prepare for edge computing discussions in professional settings. The first fundamental question asks about the definition of edge computing and how it differs from cloud computing, emphasizing proximity processing and reduced latency. Interviewers often inquire about specific latency reduction mechanisms, requiring explanation of network hop reduction and local processing benefits. Candidates should be prepared to discuss main challenges in edge computing implementations, including resource constraints and connectivity issues. Data consistency in distributed edge systems represents a complex topic requiring understanding of synchronization mechanisms and conflict resolution strategies. A typical edge node configuration includes location-specific parameters, limited compute power acknowledgement, and local storage capabilities. The process data method demonstrates how edge nodes analyze information locally before making processing decisions. These questions assess both theoretical understanding and practical implementation knowledge of edge computing concepts. Edge computing implementations face significant technical and operational challenges that require careful consideration. Technical challenges include limited compute and storage resources at edge locations, requiring efficient algorithms and selective data processing. Network connectivity issues can isolate edge nodes, necessitating robust offline capabilities and intelligent data caching strategies. Data synchronization complexity arises from maintaining consistency across distributed systems with varying connectivity and processing capabilities. Hardware heterogeneity creates compatibility challenges when deploying software across different edge device types and specifications. Operational challenges encompass security and privacy concerns, as edge nodes may be more vulnerable to physical access and require distributed security measures. Remote monitoring and management become complex when overseeing hundreds or thousands of distributed edge locations. Load balancing across edge nodes requires sophisticated algorithms to distribute workloads effectively while maintaining performance. Software deployment and updates present logistical challenges when managing distributed systems across multiple geographic locations with varying connectivity reliability. Edge computing fundamentals encompass several critical concepts that transform how organizations approach data processing and analysis. Reduced latency, through proximity processing, enables real-time applications that were previously impossible with traditional cloud-only architectures. Local processing capabilities ensure continuous operation and immediate responses even during network connectivity issues. Seamless Internet of Things integration connects diverse devices and sensors into intelligent, responsive systems. Distributed architecture patterns provide the foundation for scalable, reliable edge computing implementations across various industries. Edge computing represents a paradigm shift toward decentralized, intelligent processing that brings computation closer to data sources. As organizations continue adopting Internet of Things technologies and require faster response times, edge computing becomes increasingly essential for competitive advantage. Understanding these concepts prepares technology professionals for the evolving landscape of distributed computing and real-time data processing. Thank you for joining this comprehensive exploration of edge computing interview questions and concepts.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.